Okay, welcome again to the next lesson. Okay, now we move forward to part 3. Okay, part 3 of our model fitting and experimental modeling. Okay. Okay, so this part 3, okay, we are starting to look at how are we going to play around with the data that we have. Okay, the not so perfect data that we have. Okay, so we start with how. Okay, how to by right making sense of trying to get the best model possible. Okay, so if you notice, again, there's no one size fits all approach. Okay, meaning that if let's say you are three different people and then you approach one particular data set, okay, the same data set, these three different people, these three individual people may produce different kind of solutions for the same data set. Especially if the data set itself is a very variety type of data set. What I mean variety, maybe the duration or the length of the data set, the time series is quite expensive, or in another way, maybe the volatility, okay, the behavior of the data set itself may look a little bit tricky to see the pattern. Okay, so if let's say A by the end of the day get a data a model that representing by for example exponential function, or maybe the other person have another polynomial function. Okay, none of you guys have the upper hand, and what I mean is none of you guys are wrong or are right. The difference, okay, the difference between these three different model is just on the idea of whether your data outperform, okay, your performance of the data evaluation, okay, for student A for example, outperform the performance of model B and also model C. For example, this C student C, um, the data is poorly fit, but it is not wrong, right? It is poorly fit with the real data. Okay, so how can we able to try to get the best? Okay, that is not. If you notice, the subtitle itself reflect with what we want to achieve. Okay, we want to find the best model. We don't want to find even the correct model. By the end of the day, what is correct? Okay, in a way. So this is what we are trying to give you the skills. All right. So again, once you get the selected model, for example, once you tweak there and there, and once you improve the modeling part of it, and then the justification of your selected model, that one you need to really really emphasize and work upon. Okay, meaning that how you're going to make sure, how can you sell your idea, okay, your model, and tell other people that your model is what outperform the rest. Okay, there are some of the performance measures on that. Okay, that's why you start to look about the error estimation. Model A, the error estimation, or the MSE refer to mean square error, for example, between the model is so low, okay, compared to the previous models. Whereas on for student C, it is not so. Okay, so that is something that you need to work upon. Okay, how you're going to present your information into a more digestible manner. Okay, that is the skills that you need to really really improve upon. Okay, and then okay, so for example, how you're going to model the best? Okay, you can actually, especially you have a machine, right? You can actually, especially if you can maneuver with a polynomial function, for example. Okay, um, for example, you are so familiar with quadratic polynomial. All right, quadratic is just like a parabola. Everyone knows what is quadratic. Okay, but instead of having your data set being interpolate in a quadratic manner, you can, just tweak there and there and try to improvise by using cubic. Okay. You may think like, oh, but my knowledge is not that extensive. Okay, that is why you need to really, really scrutinize on the selection of your model. Okay, you look carefully about your data. Sometimes your data on the early part of your data, you may feel that your data behave in a way of a quadratic way. Okay, but by the end of the day, oh, actually it is not. Actually, it is not a quadratic way. In the end of the time series data, it going to, for example, the curve is a little bit changes through time, but you couldn't expect that. Okay, that's why sometimes there are also some approaches whereby you already have your data set, and then you just extrapolate certain other data set. Okay, pseudo data set based on your original model. For example, just for the sake of, you test a little bit which model fits in a long run. I mean, which data fits quite nicely in a long run. Okay, so interesting, right? Okay, so that one you need to keep on playing first, and then later once you have the real data, then only you can test again, and try to develop the best sense of model that you think you can believe in. Okay, so that is the concept. All right. Um, okay. Okay. If you notice in this slide, okay, on the third part, I mentioned over there, careful about applying the numerical criteria. Okay, what does it mean by that? Hmm. Okay, it means like this. Okay, if let's say you have this graph. Okay, the dotted line representing your data. Okay, and as usual, your model in a straight line. Okay, so if you notice over here, the straight line is your predicted model. Okay, it's like your best fitted line. Okay, everyone knows that. Okay, surprisingly enough, you can notice that the same line. Okay, the same line will represent will give you the same sum of squared deviation. Okay, meaning that, okay, if let's say you have this particular data, okay, you have data in A and data in D. Okay, these two data are completely different, isn't it? Okay, meaning that on A, on in the graph A, your data set is not quite dynamic, isn't it? Because if let's say your axis in one particular time does not move around, okay, you have three different data that is so horizontal. Okay, in the meantime, when you have your D as an illustration, your data disperse. Okay, your data disperse, and then you can see over here your straight line now. Okay, your y equals x now is actually quite a good reflective of your estimation for your the right sum of square deviation that we originally want. But if you blindly calculate only on the sum of square deviation, A, D, you get the same value. But does this representing the same thing? Of course, it does not, right? What we want is actually D, but um, but the sum of square is actually the same for your situation A, B, C, and D. Okay, so this is the thing that you have to know your data well. Okay, not it's not just that, okay, you have a data and then you put in the data inside your Excel form or inside your MATLAB, for example. You do some coding for your best estimate using whatever line or whatever assumption of the model that you want to build, and then you connect them together. By the end of the day, you calculate the deviation, and then you get the value that you want, and then you are happy. Okay, that is not so. Okay, that is not how we do the modeling. Okay, you need to revisit your data. You need to revisit ingenuity of the data, and you need to revisit, you need to question your assumptions. Okay, if let's say you already satisfied meaning that you already extensively utilize all your knowledge on whatever assessment you can do in your particular data set, then only you can move forward to the analysis. And then only you can start looking carefully on the error, on the performance based on the efficiency of the system, the time constraint that you have, and so on. And then by the end of the day, only then you can analyze it, and you can do the reporting based on what you have in mind. Okay, so interesting, right? It looks straightforward, but it is not actually that straightforward. Okay, so next. Okay, oh, sorry, next. So, this one, for example, okay, the scenario is that you are a modeler. Okay, you don't have any clue regarding the mathematical form of the model you want to know. You do not know the kind of curve that will describe the behavior, but you do know the data. Okay, so you are blindfolded by the original, the underlying model. You only have the data. Okay, your aim is to build an empirical model based on the data set. Okay, you need to find the curve. Okay, the right curve to capture the trend of the data, and you want to predict the behavior in between data point. Okay, what does it mean by the second aims? Okay, the second aim focusing more on, you are not being limited to the time frame that your data represent, meaning that you can either choose select the pinpoint in a data, in a time frame in one particular time, or you can also able now to approximate the data in the future. Okay, that is your aim. Okay, if we are able to get the by the end of the day, we get the final model. That is our aim, and our estimation should be the best one in a way. Okay, so that is our main intention there. Okay, so you can see over here. Okay, let's say you have a data set. Okay, and then your data set is in A. Okay, all right. So you have two choices, right? Okay. For example, in B. Okay, if you notice, by right, because we are so nicely put ourselves into quadratic, isn't it? Because quadratic is just straightforward and it's easy for you to identify the parameters involved in the quadratic form. Okay, so by right, you can just simply put a quadratic in cite this particular data set and see whether it match. Okay, that is one way. Okay, another way, this is the one that we normally use, the interpolation. Okay, the one that you cover normally in numerical analysis. Okay, in this way, you try to find the curve that is smooth. Smooth meaning that you are able to create a curve that tie from one data to another smoothly. Okay, it passed through the points. Okay, so you can see the example, the difference between B and C. Okay, so that is the concept. Okay, now in this case, we try to look at two different data set of data. Okay, the first one, if you notice, we have a blue fish. Okay, look at table 4.1, blue fish and also blue crab. Okay, and then for your figure 4.2, that one representing the data of your blue fish, and then figure 4.3 is for your blue crab. Okay, if you notice, okay, this the data is slightly consistent along the way. Okay, if you notice the year now, your base year, it does not talking about year 1940, 1945, and so on. Okay, why? If you notice, we try to do this. Okay, in this case, you are starting with a base year. Base year meaning that you start with year 1940 as your one. okay, and follow through. Okay, so you notice there zero would be your base point there, and then starting going through, you do the assumption of your timeline, moving forward to 4, 6, and so on. Okay, so 1940 up until 1990, you just expect it's a little bit about, maybe you can use base year into 5, 10, 15 accordingly. Okay, according to the year that you the year that you consider, and then once you put that into a data, try to make sure the data is comprehensible. Okay. Okay, so this is what you have. Okay, so you look at this one. How can you how can you solve this? Okay, how can you solve this? Okay, look at this one. We have we call that the ladder of power. Okay, so if you notice, these are the valuation to help us to do some transformation for our original axis. Okay, the transformation for our original axis. Okay, I refer you back to part two. Okay, our main intention in part two of this series. Okay, we always keen on trying to find Mm, the data that is linear, remember? The data that is linear. So the concept is here. If you want to find the data that is linear, as you can revisit on part 2, you remember, okay, what we need to do is we manipulate our original function, right? But in this case, we don't have the function yet. So how to move about, then now we manipulate our axis. Okay, we manipulate our axis. So let's say we have z as our axis, as one of our axis. So instead of having only z, we manipulate, changing our z into log z, 1 over z, 1 over z. That one is on the lower bottom. And then upper ladder, we have square root of z, and then we have z, z square, and so on. How does this help us? Okay, how does this help us? Okay, so this is the way. Okay, if let's say you imagine, remember, not remember, just focus on this is your original axis. You have y and also you have x. So meaning that by right, on a normal circumstances, your y equals to x, just a straight line. Okay, so this is your original y equal to x. Okay, you have a straight line over here. Okay, now as I mentioned there, if we transform, okay, our original y equals to x. Okay, if our y, we replace it into square root of y. Okay, set y. Okay, set y. What happened is that uh, we okay, we take out something like over here, okay, on the right hand side, and we bring it down. Okay, assuming that we bring out slowly, you can see the behavior of your straight line now becomes this. Interesting, isn't it? The behavior becomes this. Okay, that one is when you replace your y into set y. Whatever happen if you replace y into log y? You can see it becomes like this. Okay, meaning that it going down a little bit more, and then it getting slightly horizontal, but not that horizontal, but slightly horizontal. And at the same time, if you notice on the curvature of this line, now, do you think this one is a concave upward or concave downward? For example, okay, is it a concave or a concave or a convexity? Okay, so you revisit again your concave and convex, and you look at this one. Oh, I think this one is a concave. Oh no, this one is a convex. Okay, so upward or downward, for example. So this is the thing that you need to understand. Okay, that's why if you notice in math modeling, for example, you are now trying to make sense of all the knowledge that you study in your calculus, in your differential equation, and the rest of your discrete, for example, and the rest of your earlier knowledge on mathematical skills. Okay, so this is an example. This one is a little bit different compared to the rest. Okay, the rest you have a little bit concave form, and then this one, this is when you have y you replace into 1 over y. Okay, how does this help us? All right, how does this help us? Okay, so this help us in this sense. All right, if let's say you have, for example, uh, you want to make your original line like this. Okay, you want to make your original line become more linear. Okay, what you need to do, you change your y into square root of y, ln y, and other choices from the ladder of the powers. Okay, this one again you need to get your hands dirty. Just pick some random data, for example, and play around with your uh, 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 computation. Easier for you to see because this one involved with the um, illustration. Okay, MATLAB is a very straightforward ways for you to solve this. Or if you are feeling like you want to tie it with Excel, that one is a little bit limited because the function is not that much, but you still are able to solve it using Excel as well. Okay, so this that one is if you have a convex plot. But if you have a concave plot, this is another example how you are able to make it more linear. If you look at first point and the second point, you can see the different in choosing or selecting your y. Okay, so it depends on your earlier form of your formation of your illustration of this particular data set. Okay, so that's why you need to play around with this particular transformation. Okay, so moving forward, this one is quite similar to the previous one. Okay, moving forward to our data. Okay, so if let's say this is your early data, okay, that one is your bluefish example. Okay, so if you look at this one, okay, now your y becomes your bluefish. Okay, so we just assume y bluefish. Okay, so I'll show you over here. Bluefish, remember, bluefish is the one that you're going to play around with. Okay, so your original data set bluefish is like this one. Okay, and then this is what happened if you uh, choose this ladder. Okay, bluefish square. Okay, but it does not make any like a linear form, right? It just putting this one more into this, getting a little bit smoother, and then you get something like this. This is not what we want, right? And then if you choose your transformation, why you get it into the power, okay, the upper power, okay, 3, this is what you have, also does not meet with what we want. And then we start moving forward to the one at the bottom ladder and see what happens. Okay, so if let's say you transform your function into a ln, okay, ln log is just the same. It's just that ln is easier for you to calculate because it's available everywhere. Okay, log base e. Okay, so this is what you have. Even though you have something like this, and like this, something like this. Okay, but it is better, right? It looks a little bit linear compared to the rest of your example, isn't it? Okay, so once you see, oh, it's a little bit linear, then this is what you are going to choose. Okay, because our intention is we want to linearize to make it easier for us to assess later on. Okay, so It's quite interesting, right? So once you have this linearization, then only you start to choose your model based on this particular linearization. This is the model that you have. Okay, this is the model that you have. Okay, so your y now, your blue fin now is in a sense of ln y, and then since it is linear, you just equalize to mx plus b. Okay, and then you utilize the valuation of your data set, and then just plug in some information on that as what we revisit in part 2, and then you fit the model. This is what you get. Okay, so the final model is sorry, not the final model, the fitted model on regarding your loan is this one. And then the final model, of course, we want it again to y and also to x, is just to rearrange your model in logarithm into your final version of y and also your x. Okay, so basically this is what you get. Hmm. Interesting, isn't it? Okay, so basically, that's about all for this blue fish. Okay, blue fish data set. Okay, you try to do it again. You try to revisit this again. You try to do the calculation again. Okay, and then the same thing goes for your blue crab. Okay, I just give you another example so that you want to tie back with the original blue fish problem. But again, you do quite similarly, and I would recommend you to try to find another example in the books. Okay, or you can also try to find whatever data set that you have and play around with that, because if you don't do that, you didn't get the concept of what is it that we are talking about when I said changing the transformation. Okay, transform your y into another different transformation. Okay, you don't know how that affect your data set unless if you try it. Okay, so this is what you have for your blue crab. Okay, if you do a square root transformation, this is what you get, a little bit better, right? Okay, so once you do that, if you notice at this one, if you do this one is after your transformation, all right? Don't forget that this one you already transform. Once you do the transformation, you can see over here, oh, it fits quite just nicely. Okay, when you fit the model um, in the sense. All right. Okay. So if once you do all this thing, you need to go back. Okay, this is one, the one that I said, realign what you have in your mind. Okay, so once you have the same, once you did all the list estimate, okay, once you do all that good estimation earlier, you need to go back, okay, and see whether your performance is good or not. Okay, the model that you have is good or not. Okay, so that's why we have this figure 4.5 and figure 4.8, whereby if you notice, this is a superimposed data and model. Okay, you already have your model here. Okay, this is your model. Okay, instead of having ln just now, you transform your ln into a exponent valuation like this again. Okay, and then this one is a model where you have a square root in place. Okay, and then you build this model. Okay, this model is actually just this. Okay, and this model is actually just this. Okay, it is not linear anymore, right? Okay, linear just now is just your least square model. Okay, least square model whereby you have a fitted line, a linear fitted line, because that's what we want. We force our data to be linear earlier, but then by the end of the day, once you have your original, your new your new model that you already obtained, and then you know your new model y equal to blah 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 something towards your x, and then in your case in figure 4.5, your y now is just a exponent model. You build this model and you put exactly in the same axis for your data and see how it fits. If let's say you have a figure 4.5 and 4.8, if you notice, oh, it fits quite nicely with the data, even though it not exactly put inside the available data that you have, but you can see over here it not much changing. The difference between the expected data and the real data is not far away, right? Okay, it's still just nicely put with your curve. Okay, so if this is the case, then you are in a right direction. Okay, so that is how you're going to utilize your knowledge on your previous performance of the model that you decide or you construct. Okay, so boleh can Okay, so these are the summary. For example, you need to analyze your data. You need to observe a little bit of a trend. Okay, if let's say you have a very obvious outlier, okay, you can either eliminate the outlier. Okay, that one is one way. I know if you study from your statistic, normally you just eliminate your outlier, or some other approach, you can try find the average and then you replace your outlier with this average. Okay, that one is also can, some of the approach is doing that. Okay, but I would prefer, okay, if possible, if let's say it is possible for you to have the rest of your data as is, okay, it is much better actually. Okay, but sometimes things go out of our hand. There is nothing much we can do. If let's say we put the outlier inside our model and it really affect our model, then that is something that you need to consider. Okay, um but that's I leave it at that. All right. And then these are some of the summary. Okay. Um, okay, if you notice at the back, at the bottom of it, analyze the goodness of the feed. Okay, that one. If you notice, that is how we're going to assess how good is our model. Okay, that's why I said if let's say A, B, and C produce quite similar results, to decide which of these three result is much better. Okay, so you are able to investigate more on the performance of your model. Okay, so I also leave out with this one. Okay, this is a very straightforward example in Excel. All right, I tried to reduce our problem in Excel only because it is a free software. So if let's say you don't have the capacity or the accessibility using MATLAB, you can always doing your Excel. Okay, so these are the example. I recommend you to utilize this Excel to help you with the assessment of your data set. Okay, investigate as much as you want. Okay, so I think that's about all for part 3. Part 4, we are going to look at, I will touch briefly actually about the interpolation of the model that we consider. Okay, that's when you start to have a spline, for example, or that's just a bit of the information. Actually, it is a prior information, especially if you already have a little bit idea on numerical analysis. I think it's easier for you to understand. Okay, so I hope you enjoy the video and you get benefit from this. If you get a little bit overwhelmed with the knowledge in AI information, it's okay. You can always revisit this again and again. And I really recommend you to read the book, so that it is easier for you to understand. Because you know the textbook is also it has a very comprehensive explanation. Okay, it does not have the limitation of time. Okay, that's why that's time it is easier for you to uh, get more understanding on that. Okay, so accompany this video together with the text, okay, so that it will improve a lot or for your understanding in the future. Okay, so I'll see you guys in the next lesson. All the best.